Hello, YouTube. I'm Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. As usual, I'm going to talk about theoretical physics today. The topic is Heisenberg's uncertainty principle is now uncertain. This is based on a story in Science Daily back in 2012. But you'll find that your physics textbooks haven't been updated. Of course, in the reciprocal system, there is no Heisenberg's uncertainty principle. It's only a creature of quantum mechanics. You know the theory that says that electrons are in stable orbits or clouds around nuclei instead of spiraling in as they must? And the theory that says that protons remain attracted to one another by means of the strong force, when in fact we know that they'll repel one another. And also the bizarre theory that tells us that neutrons are somehow stable inside of atoms when we know by observation that neutrons are not stable. Okay, anyway, let's look at this article here. Scientists cast doubt on Heisenberg's uncertainty principle. I'm going to read this and then annotate it as we go along. Werner Heisenberg, you know him. His uncertainty principle, formulated by the theoretical physicist in 1927, is one of the cornerstones of quantum mechanics. The principle has bedeviled quantum physicists for nearly a century until recently, when researchers demonstrated the ability to directly measure the disturbance caused by measuring a property of something and confirmed that Heisenberg was too pessimistic. Well, that's true. We have practically complete control over electrons, say in the electron microscope or in televisions, etc. So, scrolling down here. Heisenberg's gamma ray microscope for locating an electron is shown in blue. The incoming gamma ray shown in green. We'll just arrow up here just a little bit. There we go. So let's just go back a little bit. Heisenberg's gamma ray microscope for locating an electron is shown in blue. Incoming gamma ray shown in green is scattered by the electron up into the microscope's aperture angle. The scattered gamma ray is shown in red. Classical optics shows that the electron position can be resolved only up to an uncertainty x that depends on and the wavelength, well, I guess I don't have the symbols here, and the wavelength, let's say lambda, of the incoming light. Okay. So, and I'm sure most of you watching this know that the Heisenberg uncertainty principle says that it is impossible to measure anything without disturbing it. For instance, any attempt to measure a particle's position must randomly change its speed. But you know what? We can account for that in the real world. And, okay, I already did that next paragraph. Okay, here's a PhD candidate. He says, we designed an apparatus to measure a property of the polarization of a single photon. We then needed to measure how much that apparatus disturbed that photon, says Lee Rosema, a PhD candidate and Professor Ephraim Steinberg's Quantum Optics Research Group at U of T, and lead author of a study published this week in Physical Review Letters. To do this, we need to measure the photon before the apparatus, but that measurement would also disturb the photon, Rosema says. In order to overcome this hurdle, Rosema and his colleagues employed a technique known as weak measurement, wherein the action of the measuring device is weak enough to have an imperceptible impact on what is being measured. Wow, what do you know? Before each photon was sent to the measuring apparatus, the researchers measured it weakly and then measured it again afterwards, comparing the results. They found that the disturbance induced by the measurement is less than Heisenberg's precision disturbance relation would require. And in fact, that disproves Heisenberg's uncertainty principle. Quote, each shot only gave us a tiny bit of information about the disturbance, but by repeating the experiment many times, we were able to get a very good idea about how much the photon was disturbed, says Rosema. The findings build on recent challenges to Heisenberg principle by scientists the world over. Nagoya University physicist Masaneo Ozawa suggested in 2003 that Heisenberg's uncertainty principle does not apply to measurement, but could only suggest an indirect way to confirm his predictions. Well, if it doesn't apply to measurement, what the heck does it apply to? A validation of the sort he proposed was carried out last year by Yuji Hasegawa's group at the Vienna University of Technology. In 2010, Griffith University scientists Austin Lund and Howard Wiseman showed that weak measurements could be used to characterize the process of measuring a quantum system. However, there are still hurdles to clear, as their idea effectively required a small quantum computer, which is difficult to build. In the past, we have worked experimentally both on implementing weak measurements and using a technique called cluster-state quantum computing to simplify building quantum computers. The combination of these two ideas led to the realization that there was a way to implement London and Wiseman's ideas in labs, says Rosino. It is often assumed that Heisenberg's uncertainty principle applies to both the intrinsic uncertainty that a quantum system must possess as well as to measurements. And I should point out, there's no intrinsic uncertainty in the reciprocal system. But the reciprocal system is not strictly deterministic. It's cause and effect. If A causes B, A might not cause all the properties of B, however. There may be some probability relations there. But that's not the same thing as uncertainty. So let's just repeat this. It is often assumed that Heisenberg's uncertainty principle applies to both the intrinsic uncertainty that a quantum system must possess as well as to measurements. These results show that this is not the case and demonstrate the degree of precision that can be achieved with weak measurement techniques. Results force us to adjust our view of exactly what limits quantum mechanics places on measurements, says Rosino. These limits are important to fundamental quantum mechanics and also essential in developing quantum cryptography technology, which relies on the uncertainty principle to guarantee that any eavesdropper would be detected due to the disturbance caused by his or her measurements. The quantum world is still full of uncertainty, but at least our attempts to look at it don't have to add as much uncertainty as we used to think. The findings are reported in the paper, a violation of Heisenberg's measurement disturbance relationship by weak measurements. The research is supported by funding from Natural Sciences and Engineering Research Council of Canada, and the Canadian Institute for Advanced Research. So there you have it. Heisenberg's uncertainty principle is now uncertain. Switch to the reciprocal system of theory and learn the truth about the physical world. You can find my work at Amazon or at transpowercorp.com. My website is www.reciprocalsystem.guru. That's where all the physics material exists. The simplest possible explanation of the reciprocal system is the mysterious universe. And most advanced is my latest work, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. And I also have 2 database modules so that the reciprocal system can be applied in practice. There's a microcosmos module. That's for photons of atoms, molecules, compounds. And there's the macrocosmos module, which is for astronomy and astrophysics. We've carried out thousands and thousands of tests of the reciprocal system, and it is now verified scientific knowledge. Of course, the mainstream scientific establishment refuses to believe it, but that's their problem, not ours. So again, study the reciprocal system and prove it for yourself. Thanks for your attention.